Hi everyone, this is a continuation of the solutions for the mid-year review, the medium questions. Okay, so this is number 6. Number 6 says, using the information below, choose all of the ways you could prove that triangle ABD is congruent to triangle CDB. So ABD is right here, and CDB is this triangle right here. And it says, given that ABCD is a rectangle and that AB is parallel to DC. Okay, so the fact that it's a rectangle is basically what's going to give us so much information that we can use almost all of these options. So instead of making too many markings at the beginning, what I'm going to do is just go through each option and make the markings for those options off the fact that this is a rectangle. Okay, so let's look at the first option. The first option is SAS. So the question is, can we find an angle and its two sides being congruent to another angle and its two sides in the other triangle? Okay, so let's go with this angle right here. Angle A and its two sides, so this one and this one, they're going to be the same as this angle C and these two sides. Now, we know that angle C and angle A are the same because they're both 90 degrees, and the reason we know they're 90 degrees is because this is a rectangle. And we know that this side, BC, is congruent to this side, AD, again because it's a rectangle, so opposite sides have to be congruent. And then lastly, this bottom side and this top side have to be the same length because they're opposite sides of the rectangle. And you can see from the orientation here that we have this angle, that side, this angle, and this side being congruent to this side, this angle, and this side. So SAS works. So we can circle that one. Side, side, side also works. We can delete some of this stuff here. So let's get rid of the angles. We don't need that. Let's delete all of these arrows. Okay, now we've already got two pairs of sides marked, and we can mark the last pair of sides, which is this one in the middle that's shared by both of the triangles. We know that that's congruent to itself because it's literally the same side. And there you go, you got all three sides on the blue triangle congruent to all three sides on the green triangle. So side, side, side works. Angle, side, angle. Okay, let's delete these two. And also, there's different ways to do each of these options. So you might find more than one way to show side, angle, side. Or you might find more than one way to do angle, side, angle. So this is the way I'm going to do angle, side, angle. I'm going to use this side. Okay. So we'll just leave that marked. And then let's mark this angle being congruent to this angle on the lower left. And then this angle here being congruent to this one over here. So that's this angle, this side, and this angle being congruent to this angle, the same side, and this angle. And they are arranged as angle, side, angle. Now, let's just prove to ourselves that these angles are actually congruent to each other, because I didn't really say why they are congruent. So let's focus on just the angles there marked with one arc in red. So the reason that, or one reason why those two angles are congruent to each other is because they're alternate interior angles. And maybe you can see the Z right here. Right? These two lines are parallel because it's a rectangle and opposite sides are parallel. And then this right here is a transversal where the two red angles are alternate interior angles. So they are congruent to each other. And then it's a similar argument for the other two. So the other two angles were, let's show them in red also. This one marked with 2 arcs and this one marked with 2 arcs. Those are also alternate interior angles, but with the other 2 parallel lines. So let's erase these 2 parallel lines, and let's draw the other 2 parallel lines from the other side of the rectangle. So AB and BC. So those 2 angles marked with 2 red arcs are alternate interior angles. So they look kind of like this. It's this one down here and this one up here. Okay, alternate interior angles. Okay, so angle side angle works. All right, angle side. So let's erase some of this stuff. All right, angle side. So we would need 2 consecutive angles and a side. Well, I've already shown the reasons why a lot of the different parts are congruent. Now we already know that this angle is congruent to this angle, and we already know that this angle here is congruent to this angle. And then we've already said that the line segment BD is congruent for both. Okay, so the markings that I made here, that shows 2 triangles being congruent by angle side. So let me just zoom out, kind of just look at one of these triangles. So I'm just going to redraw ABD, because I think one of the hard parts with angle side is just kind of noticing the actual arrangement of the different parts that are congruent. So it's 2 angles and then the unshared side. So it's one like this side over here. So this is angle side, as opposed to, I want to show you what it would look like if it was angle side angle. Okay. So this is angle side. Now angle side angle would have been, let's take the same 2 angles, this one and this one. But then if it was this side that was congruent in the other triangle, then that would be angle side angle. Okay. But that's not the one that we're doing. So we're doing this one at the top, angle side. It's 2 angles and then an unshared side. Okay. And then this triangle down here on the bottom is oriented in the same way. This angle C, this angle D, and then this unshared side. Okay. So angle side works. And again, there's multiple ways to do each one. So we could have chosen 2 different angles and a side. Okay, SSA is the only one that doesn't work. That is ASS. And that's not a theorem. That's not a triangle congruence theorem. Okay, and then lastly we have hypotenuse leg. So the hypotenuse leg is for right triangles, and since we do have right triangles, it can apply as long as we can find a hypotenuse and the legs being congruent. Okay, well, first thing we got to ask ourselves is, where's the hypotenuse of this triangle on the bottom? It's this right here, BD. It's opposite the 90-degree angle. That's the hypotenuse. Now, if we go to the other triangle on the top, this is the 90-degree angle. That implies that the hypotenuse is opposite of it. So notice that the hypotenuse is the same side for both triangles. It's literally the same line segment. So we know that their hypotenuses are congruent because it's literally the same line segment. Okay, so that takes care of the H in hypotenuse leg. Now we need to make sure that the legs are congruent, one of the legs. Well, for this triangle at the top, ABD, one of its legs is this one up here. And for the bottom triangle, no, I'll say it a different way. And this side up here is the same as this one down here. And guess what? That's one of the legs of the bottom triangle. So between these 2 triangles, we've shown that their hypotenuses are congruent, because it's literally the same line segment. BD. And we've shown that one of their legs are congruent to each other. AB and DC are congruent to each other. So that's enough to say that the two triangles are congruent by the hypotenuse leg theorem. Okay. All right, so that's it for number 6. All right, number 7. Okay, so we have to fill in the statements and reasons for this proof. So the first box here, it's one of the given statements. So if we can look here, the given statements are angle A is congruent to angle D and AC is equal to DC. AC equal to DC is already taken care of on the left here. So the only one missing is angle A is equal to angle D. Notice it says equal here. It should say congruent. So whoever authored this question wasn't too careful. But, I mean, we get the point. Okay. So that takes care of this option. That option's used. This given option is pretty easy. It's the only one left over here. Given. Okay. So now we have 2 more options left. Let's look at the next line in the proof. That line claims that angle BCA, which is right here, is congruent to DCE. Angle DCE is right here. Okay. So do we think those 2 angles are congruent? They're definitely congruent, and the reason is because they're vertical angles. So this is the vertical angles theorem. Vertical angles. And then the last line in the proof is a statement about the congruence of 2 triangles. That means that you're probably using one of your triangle congruence theorems. Now we've already used vertical angles. The only one left is angle side angle. And that's what goes in there. And you can see from the diagram that we got this angle, this side, and this angle being congruent to this angle, this side, and this angle. That implies that all of the different parts of the triangle are congruent. Okay. Delete. Next question. Question 8. Which of the following can be used to show that these triangles are congruent? Okay, so this one looks like the last one we did. For this one, this angle here and this angle here are congruent because they're vertical angles. Therefore, by angle side angle, so this angle, this side, and this angle on the triangle on the left are congruent to this angle, this side, and this angle on the triangle on the right. So this is angle, side angle. The 2 triangles are congruent by angle, side angle. Okay, done. Next question, number 9. Given right triangles ABC and DEF, where angle C and angle F are right angles, AC is congruent to DF and CB is congruent to FE. Which of the following transformations will map triangle ABC onto triangle DEF? Okay, so the answer for this one is B. So option B says a reflection about the perpendicular bisector of line segment EB. Okay, so the first thing we're going to have to do is be able to draw the perpendicular bisector of line segment EB. So where's EB? EB is right here. And then the perpendicular bisector has to intersect EB at the midpoint, which is around here, and it has to intersect it perpendicularly. So that means it has to be a line like this. Okay, and now we have to try and convince ourselves that if you reflect one of the triangles over this line, then it would land on top of the other one. Okay, so let's take the point A. The point A, if you reflected it over this line, remember that you have to come at it perpendicularly. So you have to see how far it is from A to the line of reflection, and then use that same distance directly across the line of reflection. So A should land over here on D. Okay, so far so good. One of the points of the triangle is transformed to this other point on the other triangle. All right, let's look at point C. Point C is on the bottom left. This one's very similar. You have, let's use a different color. Let's use green. This distance from C to the line of reflection has to be copied over to the other side. So that means that the point C would be reflected all the way over to F. Okay, so now we got 2 points that are being transformed so that they land on top of the other 2 points of the other triangle. Okay, and then the last one that we have to do is we have to check to see if the third point of triangle ABC, which is over here actually. Let's do it in a different color so this point B, that has to get reflected over onto E. Now this one's a little weird because it happens to be on the other side of the line of reflection. This line of reflection happens to sort of cross through the middle of the triangle, which is a little bit strange. We don't get too many examples like that. But it's still the same process. So we have this point B. We have to see how far it is from the line of reflection. It's about that far. So we have to go the same distance the other way. So the point B will land on top of the point E. Okay, so all 3 points of ABC land on top of all 3 points of DEF. Therefore, this reflection will map triangle ABC onto triangle DEF. Okay. Question 10. Use the diagram below. I'm going to chop off some of the bottom, option E, just so we can get zoomed in more. You could just rewind to see what it said. Okay, so question 10 says, use the diagram below of parallelogram ABCD, select all statements that are true. Okay, not too many of them are true here. So it says, a reflection across EG carries parallelogram ABCD onto itself. That's not true. Just quickly to show you, if we draw a line of reflection through EG, if you try to reflect A, what's going to happen is we have to travel perpendicularly toward this line. So if you draw perpendicular from A to the line of reflection, it's like this. And then if you keep going, A prime is going to be somewhere over here. Okay, obviously that doesn't land back on top of the parallelogram, so that doesn't work. Okay, so option A doesn't work. So let's cross that one out. Option B says a rotation of 90 degrees around this point. That will not work. It will be, I don't know the exact orientation, but it'll be a little bit longer up and down rather than left and right. So that won't work. Okay, let's look at option C. Option C says a rotation of 180 degrees around the point I. Yeah, that will work. So if you rotate 180 degrees, it'll end up back so that its longest dimension is oriented left to right. Okay, so that'll work. So option C works. D, the parallelogram has no lines of symmetry. That's true, it doesn't have any lines of symmetry. If it was a rhombus, then it would have lines of symmetry. Okay. Just to remind you, a rhombus would require that all of its lengths are the same. So that length is the same as this one, just about, and then this one, same length, and then this one. Now it's not that clear when you draw a rhombus this way, sort of like laying down on one of its sides, that it would have lines of reflection. But if you draw the same rhombus kind of upright like a diamond, then it's pretty clear that it would have a line of reflection. Right down the middle and directly across left to right. Those would both be lines of reflection for a rhombus. Again, it's not that clear in this picture when it's laying down on one of its sides. Okay, so it doesn't work for a parallelogram. Okay, so the parallelogram has no lines of symmetry. Oh, my bad. So it doesn't work. So that means that this statement is true. The statement is saying that it doesn't have lines of symmetry, which is true. The parallelogram doesn't have any lines of symmetry. Okay, let's go on to the next option. The next option is E. It says the parallelogram is a regular polygon, thus 360 divided by 4 is equal to 90, and we can conclude that the minimum rotational symmetry is 90 degrees. This is maybe a little bit tricky because all of this stuff from thus forward makes perfect sense. The problem is that the hypothesis of this statement, the beginning, says that the parallelogram is a regular polygon. But it's not. It's not a regular polygon. Regular polygons require that all side lengths are the same and that all the interior angles are the same. That's not the case with the parallelogram. So this is false. So we can scratch that out. So it's just C and D, at least as the options are ordered on my screen. Okay. So question 11. Question 11 says, on a coordinate plane, each point ST is defined by coordinates x, y. The segment is rotated counterclockwise to create S prime T prime. Which of the following defines a point on S prime T prime that corresponds to a point on ST? Okay, so this is just an application of the transformation rule that we learned. So we have x comma y for a rotation of 90 degrees counterclockwise. The formula is negative y comma x. So you switch the y and the x, and then you change the sign of the coordinate on the left. Okay, so that's this one. Also, it's slightly confusing the way it's worded because it might make you think that it's asking to go backwards from the image to the preimage, but it's not. It's just asking straightforward. You're going from ST to S prime T prime, and it's a 90 degree counterclockwise rotation. So it's just this rule here. Okay, number 12. This was one of the hardest questions that we've had this year. It required you to know exactly how rotations work. So let's go through the different options. It says AC is equal to A prime C prime. That is correct. This line segment is the same as A prime C prime. Because when we rotate around this point D, the shape itself doesn't change size or shape or anything. So whatever AC was beforehand, it's going to stay the same afterward. A rotation is an example of something we had, some vocabulary term we had that was rigid motion. And it means that the shape stays the same before and after the transformation. It might change location, but it still has the same size and shape. Okay, so option A here works. BD is equal to B prime D prime. Okay, so let's erase some of the stuff that we did for the first option. So BD is this distance here, and B prime D is this distance here. And the question is whether those are the same. The answer is yes, those are the same distance. And the reason is because of how a rotation works. The way a rotation works is you take this point B and you rotate it around, and you have to remember what shape is traced out as you get rotated around. It's a circle. A circle is the shape that's being traced out. So that red arc is part of a circle. And both of these blue lines, guess what? They go from the center of the circle where D is out to the edge of the circle, which makes them radiuses. and the radius is the same. Like, any radius that you draw in a circle is going to be the same as any other radius that you draw. So, yes, these two line segments are congruent to each other. The point B stays the same distance away from D as it rotates around. Okay. Next option. Option C. Measure of angle A prime DA. A prime DA. So this angle here is being claimed to be the same as C prime DC. So where's C prime? Should we do it in blue? I feel like that'll be confusing. Let's do it in a different color. C prime DC. Okay, so this angle here. So this is one of the more complicated options. This is true, so let's just go ahead and circle it right now, and then we'll explain why. So let me erase the purple one. Let's just focus on the first one. What determines how far the point A gets rotated around? What determines how far it goes around? Well, it's whatever the number of degrees of the rotation was. So if they said, oh, it's a 90-degree rotation clockwise, then it's that 90-degree number that determines how far it goes. And that determines how big this angle is, angle D. Okay. Now, what about the other one? So let's put that one back. C to C prime. What determines how far C gets rotated around to here? Well, that's the same number. It's the same number that's used in the instruction for the rotation. Now, we don't know if it's 90. I'm just making up an example. But the point is that it has to be the same in a rotation. Everything gets rotated the same amount. So the hard part here was to notice that these angles, this angle is just literally the angle of the rotation, of the rotation, the transformation. Okay, so these two, so this is already circled, that's correct. Okay, let's skip D for now. That's not going to be an answer. You know what, actually, I won't even talk about it. Let's just go to E. So E is true, and it's for the same reason. So if we go highlight it really quick, C prime is here, so C prime D C. Okay, so the question is, what is this angle? Well, that's whatever the angle of rotation was. So if they told us to rotate 100 degrees, then that's 100 degrees. And then what about B prime DB? B prime DB is this angle here. And what is that angle of what is that angle? That angle took B to B prime. So it was just whatever the instructions were for the transformation, whatever the number of degrees of the transformation was. So they're both equal to each other because they're both related to the same number, the same angle measure. Okay. All right, now these two are false. This rule is not even a rotation rule. Oh, I'm sorry, yes. No, it's not. It's not a rotation rule. If it looked like this, the y and the x were switched, then that would be a 90 degrees counterclockwise. But even if it was negative yx, we still don't know for sure that this triangle was rotated 90 degrees. We can't tell. So we can't be sure that this option is true. I mean, even worse, it's not even a transformation rule. I mean, a rotation rule. And then this is also not even a rotation rule, but even if it was, we still don't know what the exact angle was. Like, we didn't know what C prime was. We didn't know what it was. I know I wrote 90 over here, but remember, that was just like a random example. Okay, we don't know what the angle of rotation was. So we could never really decide what the rule is. Okay, so on my screen it's A, B, C, and E that are true. Option D, if that happened to be true, it would just be a coincidence. That's not something that's always true in a rotation. Okay, let's go to the next one. Okay, so it says consider the point A at negative 3 comma 5. Find the coordinates of A prime, the image of A after the transformation xy goes to negative x, negative y. Okay, so we'll start with that. Option A, find the coordinates. So the rule says just keep x and y in the same place, but just change their signs. So we originally had negative 3, 5, so we're going to have positive 3, negative 5. So that's the answer for A. So let's write that down here, 3, negative 5. Option B says, what type of transformation is x comma y? X comma y transformed to negative x, negative y. That is a rotation of 180 degrees. Now, if you're not sure, like if you don't have that memorized, then maybe it would have taken you a minute or two, but maybe you could have just played around. Maybe you could have been like, okay, well, I know that if I switch the x and the y coordinate and change the sign of the left one, then that's a 90-degree counterclockwise rotation. And if I do that again, so switch the coordinates again. All right, so we're going to do another 90-degree counterclockwise. Switch the coordinates again, so the x comes back to the front, and now the negative y goes to the back, and then go ahead and change the sign of the left coordinate. Don't forget that that's how you do a 90-degree counterclockwise. So we brought the x to the left, and we changed its sign. Notice that that's the same thing that we have up here in part B. And how did we get here? How did we get to this point? We did 2 90-degree clockwise rotations. That's a total of 180 degrees counterclockwise. Okay, so this is a rotation of 180 degrees. So this kind of awkward way, the options look, this little box here with an A, it just means to go look at list A down here at the bottom. So the options are these 4 options. And for us, it's a rotation of 180 degrees. So 180 degree rotation. Okay, option C, part C. Part C says find the coordinates of A double prime. So we've already moved from A to A prime. And we need to see what are the coordinates after we apply this transformation. Okay, so what is A prime? Actually, let's start even further back. A was negative 3 comma 5. That's the beginning of the question. We performed a transformation and we got A prime, which is the answer that we got for part A, which is 3 comma negative 5. And now they're asking us, what is A double prime after this transformation that they're giving us in part C? The transformation in part C says, up here, I'm highlighting it in red, I'm boxing it in red. It says to subtract 2 from the x coordinate and add 4 to the y. Okay, so if we subtract 2 from the y and subtract 2 from the x and add 4 to the y. Okay, so 3 minus 2 is going to end up being 1, and negative 5 plus 4 is going to end up being negative 1. So this is 1, negative 1. Okay, and then part D says write a transformation rule to map A double prime all the way back to A. So we just found A double prime. We have to write a transformation that maps it all the way back to A. What were the original coordinates of A? A's coordinates were negative 3, 5. So we have to find a way to get these numbers. 1 has to turn into a negative 3, and negative 1 has to turn into a 5. And by the way the option is given, like here's how option D is presented. notice it's x minus something and y plus something. So this is a translation. This is laid out for you in the form of a translation. So, and that's nice because you can just focus on one coordinate at a time. So we have to figure out, oh, also notice that it says minus, okay? So that means that you're expecting a move to the left, a translation to the left. Let's wait for this plane to pass. Okay, and that's nice because it's the x-coordinate is at +1, but then it ends up at -3 down here on the right. So how far to the left do you have to go for you to go from +1 to -3? You have to go backwards 4. So this would be x minus 4. I'm writing in the answer on the left. X minus 4. And what about the y value? We need the y value to go from -1 to +5. That means we would have to add 6. So we add 6 to the y coordinate. Okay. So that's it for that one. Next. 14. The regular polygon below is rotated about its center. Which angle of rotation will carry the figure onto itself? Okay. So what makes this question a little bit tough is the fact that some of you might remember the formula that if you take a full revolution, which is 360, and you divide it by the number of sides, and it's a pentagon. By the way, this equation only works for regular polygons. Regular meaning that all the side lengths are the same, and all of the interior angles are the same. Basically, it amounts in these polygons that look very symmetrical, okay? As opposed to any other random pentagon. Like you could have a pentagon like that. It's 5 sides, but it doesn't look symmetrical. So this formula down here, if you do 360 divided by 5, you get 108. Wait, is that right? 108 times 5 is 40. 0, put the 4. No, it's not even close. Oh, that's right. This is 72. Sorry, no calculator. Okay, so 360 divided by 5 is 72. So that tells you that if you rotate this polygon, let's put a center of rotation in there. If you rotate 72 degrees, okay, then this point in red at the top gets moved over to this point over here. Now 72 represents the minimum amount of rotation. And if you notice, 72 is not one of the options. So that's a little bit confusing, but that's because 72 just represents the minimum amount of rotation. But what if you took this 72 degrees up in the picture and you just added another 72 degrees so that the point moves to the next spot? Basically, you're just kind of rotating this pentagon little by little every time. So this is another 72 degrees. What's 72 plus 72? 72 plus 72 is 144. So you can also rotate this pentagon 144 degrees and it'll still land on top of itself. But notice 144 is not over there. Okay, but you can rotate another 72 degrees. So we're going to take this corner, rotate it another 72 degrees so that it lands here, right? All of the points move around as you rotate 72 degrees. Okay, so if we add another 72 to the 144, that gives us 216 degrees, which is actually right there. It's option C. So you could have rotated the pentagon 216 degrees. The little bit of confusion here is that people are used to just doing this formula and getting the minimum amount of rotation and then just stopping. But that's just the minimum amount. Every time you do the minimum amount, the polygon lands back on top of itself. Okay. Next question, number 15. The figure below shows a rhombus. Okay, so from earlier in the video, one of the things we talked about is that for rhombuses, if you reflect over the diagonals, then the rhombus will get carried back onto itself. Okay. As opposed to a parallelogram where it doesn't work. Okay, so this one's asking which transformation would not carry the rhombus back onto itself? Would not. Okay, reflection over the shorter diagonal, that would work, so it doesn't answer the question. So let's scratch that out. A reflection over the longer diagonal, that would also work, so that doesn't answer the question, so let's cross it out. A rotation of 90 degrees doesn't work. It sort of looks a different way. So on this bottom right corner, you can see we have the obtuse angle. If you rotate 90 degrees clockwise, then you could think of it as the rhombus kind of falling over here. And it's going to look a little bit different. The rhombus is going to look like this instead, where this bottom right corner is now the acute angle. So it won't really land on top of itself. Okay, so that doesn't work. And then it says a clockwise rotation, option D says a clockwise rotation of 180 degrees about the intersection of the diagonals. So 180 degree clockwise rotation, that would work. Okay, if you did this one more time, then this angle, this obtuse angle, would be the one that ends up on the bottom right. Whoops. So we have the obtuse angle down here. That means that the rhombus would look like this. Okay, which is the same orientation as it was originally. Okay, so that one works. Oh, and I forgot what I was actually answering. D works, which means it doesn't answer the question. The actual answer to the question is C. This was the one that doesn't work. Okay, anyways, you saw why D does work. Okay, so C is the answer here. Delete. Question 16. Write the equation of the line that would map the trapezoid onto itself. So the only line that would work as a line of reflection here is a line that goes right through the middle of the trapezoid here. The dark blue line that I just drew. This light blue line was just some kind of mistake in the picture. Okay, so then all we need to do is write what the equation of this line is. This is the equation y equals 2, so that would have been the answer. Okay. Going. 17, which of the following statements must be true? We're only choosing one of these. Line M is the perpendicular bisector of line segment BB prime and line segment CC prime. Okay, well, first of all, we have to identify what these line segments are. So it says that we're reflecting over the line M. So we gotta take B, it's about that far, which is about to here. So B prime is over here. And then C, we have to reflect that across the line. It's something like this. Okay, this is C prime. Let's, I'm gonna leave these two lines because they help identify what the solution is. So the solution is A. A says line M is the perpendicular bisector of line segment BB prime. So BB prime, the line segment BB prime, is this one up here that I've drawn, the long one, all the way across. From one side of the line of reflection all the way to the other side. That's BB prime. And the question is whether M is the perpendicular bisector of that line segment. The answer is yes. How do we know? Well, what is a perpendicular bisector? What does M have to do in order to be the perpendicular bisector of BB prime? It has to cut it directly in half, so this length has to be the same as this length. That's true because the way reflections work is you figure out how far B is from the line of reflection, and then you recreate that same distance on the left when you reflect it over. So by the way we do reflections, it's true that these two lengths are the same. So far, we got the bisector part. Now, what about the perpendicular part of M being the perpendicular bisector? Well, that's also a consequence of the way we do reflections. This line right here that I drew showing the distance to the line of reflection, the way I drew that line was like this. I went from B straight over, and what I mean by straight is that this is 90 degrees. Like, I didn't do something weird like this. Like, I didn't approach the line M from B in some random angle like this. Okay? You have to approach it perpendicularly. Oh, so that means that is 90 degrees. So, yes, M is the perpendicular bisector. And the statement says not only is it the perpendicular bisector of B prime, but it's also the perpendicular bisector of C prime. And it definitely is, because you have to do the same thing with C that we did with B. Okay, so A is the answer there. None of the other options have to be true for a reflection. Okay, next question, number 18. Which rotation about its center will carry a regular decagon onto itself? Okay, so a decagon has 10 sides. So that means we'd have to take, and it is a regular decagon. That means that we can use the formula 360 divided by the number of sides. In this case, it's 10. So a 36-degree rotation would take a decagon onto itself. Now, unfortunately, 36 degrees is not one of the options. But that's fine. 36 is just the minimum rotation. But every time you rotate by another 36 degrees, the decagon keeps landing back on top of itself. Okay, so if we just add 36 a few times, then we should reach one of these numbers. Another way to do it is to start at 360. So if you start at 360 and you subtract 36 a few times, you should also land back on the number. So I don't really remember which way. Well, I think 198 is the answer. So let's see, does 36 go into 198? I think 36 times 6 might work. So 36 times 6. 6 times 6 is 36. Put the 3 up here. 6 times 3 is 18. Plus 3 is 21. Nope, that didn't work. What about 36 times 5? I should have just used a calculator. 6 times 5 is 0. That's not going to work either. Okay, let's just add 36 over and over again until until we get one of these. Alright, so 36 plus 36 is 72, plus another 36 is 108, plus another 36 is 144, that's not there, plus another 36 is 180, that's not there, plus another 36 is 216, oh my goodness, plus another 36 is 252, okay, there it is, so 252. Okay, next question. Number 19, which figure has 90-degree rotational symmetry? That would be a square. A square for sure has it. I mean, I think some of you guys kind of know that just because it's one of the more basic shapes that we work with. If you rotate this 90 degrees, then it'll land back on top of itself. All of these points get moved over. A more technical way to do it is to take a full revolution, which is 360. Notice that all of these are regular, right? A square is a regular polygon. Here it says regular hexagon, regular pentagon, and equilateral triangle is also a regular polygon. All the side lengths are the same and all the angles are the same. So for all of these, you can apply the formula, 360 over the number of sides. 360 divided by 4 is 90, so that corresponds to a square. So A is the answer. Okay, number 20. Which transformation will carry the rectangle shown below onto itself? Okay, so diagonals don't work. Reflecting over a diagonal, like this line M, does not work for a rectangle. Remember, it does work for a rhombus, and it does work for a square, but it doesn't work for rectangles. This would be a square. If it was a square, the diagonals definitely work. Okay, and for a rhombus also, but not for rectangles. Okay, so a reflection over line M for option A, that doesn't work. A reflection over the line y equals 1. Y equals 1 is a horizontal line going through a height of 1. This is the line y equals 1. And that looks like it works. Let's just count how much of the rectangle is above. So starting from here, we got 1, 2, 3, 4, 5 units here. And 1, 2, 3, 4, 5. Yeah, so this is directly halfway. So if you reflect the rectangle over that line, then it would land back on top of itself. So B is the answer. Option C, a rotation of 90 won't work. It'll be oriented so that the longer side is facing up and down, like this. So that won't land back on top of itself. And 270 would actually kind of be similar. It'll be rotated and it'll be oriented in the same way with the length, the long side up and down. Okay. Number 21. Which transformation will place the trapezoid onto itself? This one will be a reflection across the y-axis. Okay, so a reflection across this line will work. Why will that work? So remember, when you do a reflection, you can always just go to the individual points. Sometimes you don't want to think of reflecting the entire object because maybe it's a little bit confusing. So you can always just go to the individual points of the object. So we can go to this bottom right corner. If you reflected that over this line, the y-axis, then you have to see how far away it is perpendicularly. Okay, and then you can see that this distance is the same. Now, if you're saying, but Delamo, how do you really know how long that is? Like, how can we be certain they're the same length? Then you can actually go ahead and look at these coordinates. So, you know the y-axis is 0, 0, okay? And then it says here that this is 4, -3. So it's 4 units to the right of the y-axis. And then this other one is -4, -3. So it's also 4 units to the left, though, of the y-axis. Okay, so that's how we can tell that this is 4 units and this is 4 units, so they're the same distance. Therefore, you know, it definitely got reflected over to that point. And then you can take this point over here, and you can reflect it over, this is 2 units, this is 2 units. Okay, and then you could take any number of individual points you want along this end. But at this point, it's enough to just connect the dots. Okay, so D works. Option D on my screen. Okay, 22. A parallelogram has vertices 0, 0, 0, 6, 4, 4, and 4, -2. Which transformation maps the parallelogram to itself? Okay, we cannot use reflections for a parallelogram unless the parallelogram happened to be a rhombus or it happened to be a square. But this parallelogram is definitely not a rhombus. It's got kind of a longer dimension up and down than it does a width left and right. So it's definitely not a rhombus. So we're not going to be able to reflect across any of these lines. So we can scratch these out. Option C says a rotation of 180 about the point 2, 2. Option D says a rotation of 180, but about the point 0, 0. Okay, so the answer is a rotation about the point 2, 2. That means that this would be the center of rotation here, and the parallelogram would rotate around. This other point here, 0, 0, that wouldn't work. Okay, you can just think of this point on the top right. Let's call this point A. When you rotate 180 degrees, you move one quadrant. So, I'm sorry. When you move every 90-degree rotation, the point moves over one quadrant. So A would have moved, after 90 degrees, A would have moved over here into this quadrant. This is 90. And then after another 90, which is 180, which is what they're saying in option D, it would have moved down into this one. And if it did move down into this bottom quadrant, the parallelogram is not there. It's only in quadrant 1 up here. Well, and a little bit in quadrant 4. But to land down here in quadrant 3, it wouldn't even come close to landing on top of itself. Okay, done, delete. 23. Which transformation can map the letter S onto itself? Okay, so here's the letter S. That's pretty bad. Try it a little bit more symmetrical. A reflection will not work. Here's one reflection. Upside down, it would end up like this. Here's another reflection, but like being reflected left to right. It would look like this. Actually, they will both look the same. Both reflections. Whether you reflect across like a y-axis or whether you reflect across like an x-axis, neither of them will, like the S will have been flipped around. It won't land back on top of itself. So a reflection won't work. So we can get rid of reflection. A translation won't work because it'll just move. It'll move away. It won't land on top of itself. A dilation won't work because it'll grow or shrink. So you might end up with a little S like this or a big S. And it won't land on top of itself. And then a vertical stretch we never even talked about. But that would be like, it gets extended just height-wise. So it'll be like longer up and down, but it would still stay the same width. So if this was the width before, it's still the same width after. It just got stretched vertically. Yeah, we never talked about that. And then the last option is rotation. So yeah, a rotation would work. If you take the letter S and rotate it at 100 degrees, you could try it. Like if you're on your phone right now, or if you're on a tablet and you just turn it upside down, you'll see that the S looks the same way. It looks like that when you rotate 180 degrees. This is for rotating 180 degrees. Okay, so rotation works. 24. So in this one, I'm not going to read it. It says that, in short, it says figure 1, we go through a couple of reflections, we end up here, and then another reflection, we end up here. Could we have just done one single transformation to get figure 1 to figure 2? And the answer is yes, we could have just translated. Okay. So we could have just moved this figure across all the way over there. The key here is that the lines had to be parallel for that to happen. and they mentioned that at the top. If they weren't parallel, then it wouldn't work. Okay, 25. This one, when we did this problem way back at the beginning, I showed you by trial and error how to do it. Like when we remediated it after the quiz or the test, wherever this problem came from. I showed you how to do it by process of elimination. So, I think I'll do that again. Yeah, let's do it that way. So it says that we're rotating around the point 1, 1. Now, unfortunately, since we're rotating around the point 1, 1, that means we can't really use the transformation rules for rotation. So we cannot use, this would be negative y, x. We can't use that. Actually, it says clockwise, so it will be the other rule. Let's erase this one. That's the other way, where, you still switch the x and the y, but it's the coordinate on the right that gets the negative. We can't use this. We cannot use this. This only works for rotations around the origin, 0, 0. But here we're rotating around this point, 1, 1. Okay, so what we're going to have to do is use something that we know about rotations. So one of the things that we know about rotations is that the distance from the center of rotation to the point stays the same as the object gets rotated around. So this point A, let's use blue. It will stay the same distance. Okay, all of these points stay the same distance away. So we're basically going to use that to eliminate a lot of these options. Okay, so in each of the options, they show the original. Oh, geez, I didn't take a